morning, friends. Let us have a relook on the example where we were calculating wing loading. And if you recall, the mission requirements were V max greater than or equal to 130 knots, then takeoff distance less than or equal to 1,000 feet, then rate of climb greater than 1,500 feet per minute, and of course Vstall less than or equal to 50 knots. And we have selected an engine based on the baseline airplane, and that power loading W by HP was around 8. Right? And if you see, when you calculated wing loading for different conditions, we got conditions, if I write here, was stall one condition, takeoff was another, climb, and then cruise. These 4 parameters we have considered just for an example to see how we're going to use it. And we got W by S for this is 10.2 pound per feet square, and this is 14.9 pound per feet square. Climb, it was 62 pound per feet square, and this was 20 pound per feet square. Of course, this should be less than equal to less than equal to less than equal to this. And in kg per meter square, if I convert, I get this around 49.8 kg per meter square. Please see the conversion, whether they are correct or not. 72.75 kg per meter square, and this is 302.7 kg per meter square, and this was around 97.6 kg per meter square. Now you could see that so many values of wing loading we need to have to satisfy the mission requirements, which are in terms of stall, which cannot be more than 50 knots, takeoff, which cannot be more than 1,000 feet, climb minimum 1,500 feet per minute, and when you are doing a cruise, we are taking around 130 knots cruising speed. Vmax could be more than that. Now, if this is the condition now we have, different values of wing loading we are having, which one I should pick? That's why I was telling, first of all, we should know, and we know, what type of aircraft we are designing. If it is an aircraft which has range to be the most predominant thing, then I will look for, I'll give more weightage to the cruise conditions. And let us say I give weightage to cruise condition. It tells me that W by S should be around 97.6 kg per meter square. And it goes without saying what we are meaning thereby, that is W by S here is 97.6 kg per meter square, or 20 pound per feet square, which actually means you know how to convert it back to W by S takeoff, right? You know how much fuel is consumed here to here and here to here, divide by that fraction and you get W by S takeoff requirement for cruise mission. Right? This is, we know it. But today we are discussing something different. When W by S cruise is this, if I want to see whether my stall conditions are meeting or not, then I find for stall which is a limitation of 50 knots, cannot be more than 50 knots, it tells me it is around 49.8 kg per meter square. And if I select W by S based on cruise, it tells me I will have W by S as 97.6 kg per meter square, and which when I convert back to the takeoff from here, it will be a little more than this, right? It may become 120 kg per meter square. Now the point here is very simple. If I take W by S as, let's say, 110 or 120 kg per meter square, then problem is how it is going to affect your stall. See, as far as stall is concerned, V stall is 2 W by S by rho CL max. Right. W by S we have picked the value from cruise, which is appropriately corrected for takeoff, right? V stall I want around 50 knots. So if I take W by S as 97.6 kg per meter square, then naturally your V stall will be more because it varies with W by S. To maintain the V stall, the W by S required was 49.8 or less than that, but we are selecting 97.6, which is more than as dictated by stall condition, which actually amounts to that the V stall will increase, keeping everything constant. But that is a condition you cannot violate. So what is to be done? That is the question. If you see in the example of a Raymer, they have used no flap condition, right? And they have taken CL max as 1.4, around that. But in this example, I have already assumed that there is a plain flap. Because I understand that normal airfoil, CL max of 1.2 is a good initial number to start your job, right? And once you use the plain flap, if you give a deflection by 10 degrees, flap deflection, you can easily touch 1.4 CL max. But then, coming back here, if W by S has increased, but still you want to keep 50 knots, or around 25 meter per second, and keeping W by S as 97.6 kg per meter square, density remains same place you're taking off, which will amount to how much CL max is required. So that CL max will definitely not the CL max used here. So in this case, if you have to maintain this, CL max has to be increased. Then you check how much CL max is required. How much? And see whether that enhancement in CL max I can get by further deflecting the flap or not, or using a little higher order of flap or not. Right. So this sort of a debate will go on. And if it is making life miserable in terms of, which is affecting every other parameter, then you have to take a look whether I can play around with this or not. Right? We'll solve an example. This is just to show you what sort of issues are coming. So if I could immediately see a conflict in maintaining stall condition and cruise condition, right? Next we see what happens if I take climb condition. You see, if you are to maintain the climb 1500 feet per minute, it tells me two things, that T by W should be around, if you check your notes, T by W will be around 0.465, yes, 0.465, because as per the climb rate is concerned, or rate of climb is concerned, which was 1500 feet per minute, and we plan to climb at 70 knots, which is 35 meters per second. we got G as 0.212, right? Which was ratio of vertical velocity with the climb velocity, roughly, right? So now the question is, if I have chosen cruise, W by A is 97.6, let's say I have chosen cruise at 97.6 kg per meter square, but climb requirement is around 302.7 kg per meter square. What is the implication of it? If you see, we write W by S less than equal to T by W minus G plus minus under root of T by W minus G square minus 4 CD naught by pi aspect ratio E. This W by S of 302.7 kg per meter square we got by taking T by W at 0.465. So now if I put W by S as 97.6, because that if I am choosing, which may be around 100, I told you, when I convert back to takeoff conditions, then, of course, this I have to multiply it by 9.8 to make it Newton per meter square to be consistent with the unit. If I do that, then I can find out, keeping everything same, what is the T by W requirement, right? And from here, if I find T by W is some value A star, but we have seen T by W equal to A star, which I am getting by putting the W by S as whatever is prescribed by cruise condition. I put that value here, and I find what is the T by W coming from this expression from here, keeping everything same. This T by W, I now check back with 550 into neta P into HP by W, right? Okay. And see what is the HP by W required, or what is the inverse of power loading required, whether I am able to get from that engine or not, right? So this sort of an iteration will go on, right? And you will see when we actually solve an example, this thing will become crystal clear. Similar thing you will find with takeoff distance. If you see, if I take the cruise W by S, which is around 97 kg per meter square, and for takeoff distance it is around 72.75 kg per meter square. So immediately you know I will be able to satisfy takeoff conditions if I take a cruise condition. So this doesn't bother you much. What bothers you is this one, and to some extent this one. Right. Okay. But that sort of an iteration is a must, and we have to do that. Also understand one more thing when I closely see the cruise data, which will help you in making a decision. Let's be careful about what is the cruise W by S we are talking about. How did you calculate cruise W by S? We assumed the dynamic pressure as 35 pound per feet square, right? It amounts to some altitude, right, which you can find out because you have an idea about what speed I am going to do. But if you see, when I calculated W by S for cruise, what I have done, I have taken Q infinity under root pi, aspect ratio, E CD naught, right? And what is this condition? This condition is for maximum range, where we are assuming CL equal to under root CD naught by K. From that this expression has come. Aspect ratio at conceptual stage, you have some number, CD naught 0.02, and CL is fixed, CD naught by K. Now I ask a question to myself. When I'm writing Q infinity as 35 pound per feet square, with the dynamic pressure. So Q infinity is half rho V infinity square. So I know through dynamic pressure what is the combination of rho and V infinity. If I want to tweak this W by S, suppose I want to see that W by S, I want to increase from 100 to 150 so that I can do a compromise. That only way I can do it is I change the dynamic pressure, which in turn means either I come little lower altitude, which you may not like, or you increase the speed. But then for speed, you know that for speed, maximum is 135 knots. And we are trying to evaluate cruise at around that speed. So that's the problem. And suppose it demands that you have to decrease 97 from 97 to let's say 70, the option could be primarily you reduce Q infinity, or that means keeping the speed same. One option could be you go higher altitude, then it will reduce. But then if depending upon type of engine, type of navigation available, type of air traffic controller clearances for a generic aircraft of this type, much variation in the high end altitude will not be permitted. You know, you cannot go beyond that. You will not get. So all this sort of a conflict will come, and finally we'll have to pick one, and then we start calculating the mission performances with that. For example, let's say we're doing all this compromise. Let's say we fix W by S as 110 kg per meter square. Okay? Generally, if you read a book, the thumb rule advice is always you take the lowest wing loading. Lowest wing loading here is which one? Stall, 49.8 kg per meter square. Why it is recommended lowest wing loading means larger wing area, right? So that is, but you understand larger wing area means larger span, because you need to have a larger aspect ratio. Larger wing area means larger drag. So all those complications come, and then the question is, if the lowest wing loading criteria I am selecting, I'll cross-check what is the mission performance it is satisfying. It is stall. My airplane, if the requirement is very stringent on takeoff condition, then I may give wing loading as a primary importance. As long as I am exhausted with all the CLmax or high lift device options, right? If it is a plane for maximum range and all, then why should I give so much weightage to this, right? So that sort of a debate will go on. And let's say W by S is 110 kg per meter square, we have decided. Then what we have to do, we have to again go back to our question, Vmax 130 knots, then takeoff distance less than 1,000 feet, rate of climb greater than 1,500 feet per minute, and Vstall less than 50 knots. So with this new wing loading, we'll check whether these mission requirements are meeting or not. Few you'll find okay. Few again you have to see what additionally I can change to make a compromise and near optimized solution I get. Especially in cruise, you need to also understand when I wrote cruise as the expression based on maximum range, which was Q infinity under root pi aspect ratio E CD naught, right? This assumes CL equal to under root CD naught by K. So if you have chosen an altitude where you will be cruising primarily, then half rho V cruise square SCL will be equal to weight, or V cruise will be 2 W by S by rho CL means CD naught by K. So you could see that your V cruise gets fixed for a given wing loading, which is for range to maximum. But you have to check whether this cruise speed is what a customer is looking for. He may say, oh, come on, this speed is very low. Or you may find this speed is coming very, very high. That will have a lot of structural implications. Generally, you'll find it come low. So then what to do? Then again, you try to alter the altitude, or you then compromise. You say, okay, I'm sorry, I'll be getting this W by S by giving more weightage to cruise speed. And accordingly, I will look for CL. It will not be really a condition of minimum or maximum range. But ideally, what one will do, we'll try to select what altitude I select, still I fly with this, and my cruise speed is acceptable. You can see that if I reduce rho, cruise speed will increase, right? So I can always do that sort of iteration that, okay, I pick up an altitude where I get a higher cruise speed to maintain lift equal to weight, flying at CL equal to CD naught by K, will satisfy my customer also, okay, it's not that too slow an aircraft. So all those implications will come, and finally you take one or two. That's why in design, you at least have 2 to 3 configurations moving parallelly as far as wing loading is concerned, right? And create a huge database. For example, if I want to create a database, I'll create a database for W by S for different dynamic pressure, different aspect ratio, different CD naught. Well, all those should be available with me. So whenever a crisis is there, I can pick up them and use a linear interpolation method to get my configuration. Okay. After cruise, if I need to discuss something on climb, you'll find this rate of climb, whatever we have prescribed maximum rate of climb. To maintain that, this is 1500 feet per minute. To maintain that, you need an excess power at different altitude. As we are going higher and higher, this gentleman comes down and this goes like this, so your excess power reduces, right? So if you are trying to ensure that, yes, it should have a particular rate of climb, let's say rate of climb, say a B star, this much rate of climb at this altitude, right? To be more specific, suppose I want rate of climb maximum, it is 100 feet per minute at rho sea level, or sorry, service ceiling. Right? What is service ceiling? Service ceiling is that altitude at which rate of climb is 100 feet per minute. Right? That indirectly tells you up to what altitude you can climb. Right? Because whatever climb rate you have at the sea level, as I am going up and up, amount of air is reducing, so your engine will not develop or deliver that much of power which was available at the sea level. It will go on reducing. And also the power required graph also changes, you have seen. And so excess power reduces, right? So how do I ensure the rate of climb maximum of 100 feet per minute at particular altitude, which is service ceiling? We sometimes, since there's air is going down, in particular oxygen is going down, so you can use some sort of a turbo charger. If you see our Hansa 3 airplane, they use this during that altitude. It's operational, right? However, this costs money, right? Efficiency goes down. But yes, we have to go to that altitude, so there are provisions of turbocharger, supercharger, etc., associated with the engine. That also, not only that helps in getting a good service ceiling, but also this creates maintenance issues. You have to be very particular about it. Apart from that, beyond an altitude for a non-pressurized airplane like Cessna 206 and all, you need to ensure that there is an amount of oxygen in the cabin so that pilot and passengers are comfortable, right? So you will find many such altitudes people are flying, the pilots and co-pilot combination are flying, they carry oxygen cylinder, oxygen mask with them, right? So just for a conventional general aviation aircraft, we start thinking of altitude. You should not only think in terms of excess power, or you should not think in terms of wing loading, thrust loading, or CL max. Please remember, as I go higher and higher, the amount of oxygen goes down, and that has to be handled. The pilot needs to have some oxygen for keeping himself alert, right? So that sometimes decides whether you are going to fly at that altitude or not, okay? Because it adds to cost. That's very, very important, right?